Hello and welcome to Water Quality. In this video, I'm going to show an example of complexation using ferric chloride. So ferric chloride, when it's added to deionized water, is going to form ferric iron, which is Fe3+, and that complexes with hydroxide. So we can describe this complexation both as an acid reaction and also as a complexation reaction. And ferric chloride is a very important chemical in environmental engineering because it's often used in water treatment as a coagulant, which is a topic that we'll cover in subsequent videos. Okay, so to start with, we add ferric chloride to deionized water in this example, and it completely dissociates. So we have ferric chloride releasing a ferric iron ion, and then also 3 chlorides. And this is going to um, have 100% ionization. So that's my first reaction. Then ferric iron is going to react with water and form a complex with hydroxide. So I can show that as Fe3+. So it's essentially complexing with the hydroxide that's from water. And it forms FeOH2+ and releases a hydrogen ion, which makes this an acid reaction. And so we can describe this as a Ka describe it with a Ka equilibrium constant, and we're going to denote it as 1 because this is the first release of a hydrogen ion. Okay, and I'm going to write out the equilibrium constant here, or equation. So I have FeOH2+ times hydrogen ion over Fe3+. Now I can also write this as a complexation reaction, and the way that I do that is to add this reaction to the water equation, but I'm going to flip it. So I do that by putting water on the right side and my hydrogen and hydroxide ions on the left side. And so then I describe this as 1 over kW, or 10 to the positive 14. Okay, so I'm going to add those first are these two reactions. So if I number these 1, 2, and 3, I'm going to add 2 and 3 together. Okay, so right away you can see that the hydrogen ion cancels out, as does the water. And what I'm left with is my ferric iron ion reacting with a single hydroxide and forming this ferric hydroxide complex, FeOH2+. And this I'm going to describe with a stability constant because it represents a complexation where the metal is reacting with a single ligand, and I'm going to call it beta 1 because it is a single ligand. And this one I looked up on a table of stability constants using the water chemistry book by Snoyak and Jenkins. And so this, I have a value of 10 to the 11.84. Okay, and also I know that when I add two chemical reactions together, I take the product of the equilibrium constants. So I have Ka1 over Kw here, and I can solve for the Ka value. So Ka1 is my beta 1 times Kw, and I get a value of 10 to the minus 2.16. or pKa, you can write that, pKa1 of 2.16. And this is important because what it tells me is that Fe3 plus, or ferric ion, is the dominant species of these two species when the pH is less than 2.16. So only when the pH is less than 2.16 is the Fe3 plus going to be dominant, and then above, so pH greater than 2.16, which would be most waters, most natural waters, the ferric hydroxide complex is dominant. Now, of course, here we're just considering two different species. We haven't included other ferric hydroxide complexations. We're only considering these two species. And of course, ferric is going to react with more hydroxide and form other complexes. And for that, we'll go to another video.